We're going to do our final example now. So if we've got 2 liters of water on a stove that's currently at 20 degrees Celsius, how much heat energy Q do we have to put into that water to bring it to boil? How much more heat energy will we have to put in to boil off all the water? So first thing to notice, we don't have liters as mass. We just got 2 liters of water. But if we're dealing with standard room temperature water and standard pressure, which we are, reasonably thing to assume since we're dealing with a stove, we can convert that, since 1 milliliter of water is the 1 milliliter of water at standard atmosphere and pressure is the same thing as 1 gram of water, then a liter of water is the same thing as 1 kilogram. So a liter is equal to a kilogram of water. So if a liter is equal to a kilogram, then 2 liters is equal to, well, liter's not equal to kilogram, but liter goes to kilogram when it's in terms of water. So 2 liters goes to 2 kilograms. So we've got a mass of 2 kilograms of water, which we're going to need to use to be able to do any of this. So also, what's the specific heat for water? Specific heat for water is equal to 1 calorie per gram per Kelvin, right? So if it's 1 calorie per gram per Kelvin, well, that's the same thing as 4.1868 joules per gram per Kelvin, right? So 4.1868 joules per gram per Kelvin, right? But if we want to do that, we can also upconvert that to kilograms. 4.1868 kilojoules per kilograms, kilo both on the top and the bottom. Great. So now we've got, that's what our specific heat is. That's how much energy it takes in to be able to raise it 1 degree. So if we need to get from 20 degrees Celsius to 100 degrees Celsius, what's our change got to be? Our change in temperature is going to be equal to 80 Kelvin, right? Since a Kelvin and a Celsius are the same thing. So we're going to start boiling once we hit 100 Celsius. But it'll take a lot more energy because we have to then push over all of that extra energy to be able to actually get over that line, to be able to get all of our liquid over the line into the gas phase. So we're going to need even more energy on top of just getting it to 100 Celsius. So change in temperature equals 80 Kelvin. Our formula is the amount of energy that we have to put in to get a given temperature increase for a given substance is the specific heat of that times the mass we're dealing with times the change in temperature. So our specific heat is 4.1868 kilojoules per kilogram. So it's 4.1868 times 10 to the third, since we're dealing with kilojoules, times the specific the mass we're dealing with is 2 kilograms times the change in temperature is 80 kelvins. We hit that with a calculator and we need 669,888, way too many significant digits, and so that becomes 670 kilojoules. So we need 670 kilojoules of energy to be able to move 2 liters of water from room temperature to a boiling temperature. But that's not enough energy to be able to actually get rid of all of it. From there, we now have to use the heat of transformation. The heat of transformation to get from liquid into gas, the heat of vaporization for water, is 2,257 kilojoules per kilogram. So if that's how much it is, we're going to use heat of transformation is equal to L, our coefficient of transformation, times the mass we're dealing with. So L is 2,257 kilojoules, so kilo times 10 to the third, times 2 kilograms. We get 4,514,000 joules, which is then the same thing as 4.154 megajoules of energy. 4.154 megajoules of energy, that's more than 6.7 times energy. So it takes way, way more energy to get it to actually boil off than it does to get it to the point where it can just begin to boil. Because as we add in a little bit of energy, a little bit of the water will manage to boil off. But to be able to actually boil off all 2 liters, it takes well more than 6 times, almost 7 times more energy. And we're not even including the fact that we're going to actually lose some of this heat energy, right? It doesn't all perfectly go into heating the water. As it's at a hotter temperature, it's going to be radiating more heat greatly to the area around it. So it's going to take probably even more than 6.7 times energy to get that water to actually boil off. That's a huge difference, right? And that's the reason why you can bring water to a boil, toss in your spaghetti, and come back and not have all the water gone, is because it's actually going to take, if you assuming a constant amount of heat going into that pot, it's actually going to take more than 6 times the amount of time to get it to go from starting to boil then to all the water gone. So if it takes you 10 minutes to bring a given amount of water to boil, you know you've got at least an hour before all of that water will have wound up boiling off. So that's a really interesting thing to think about. And that specific heat of vaporization is also one of the things that's so amazing about water. That high specific heat of vaporization means that we can have things like sweat happen, where the amount of heat in our skin gets transferred into the water, and since it has such a high vaporization heat, we're able to transfer lots of energy into it and have it get wicked away into the atmosphere. And so we're able to conveniently, usefully cool ourselves because of this high vaporization heat for water. One of the really cool things that water gives us. All right, hope you enjoyed that. Hope it made a lot of sense, and we'll see you later. Bye.